Okay, so good evening everybody. So, we will continue with this week's discussion in this course FAST Fundamentals of Aerosecond Science and Technology, which we bring to you from IIT Madras and IIT Tirupati. So, this is we are closing out the module on femtosecond laser pulses. We are in the 10th session we are holding for this module. And let us proceed where we once again refer to key texts, the book by Roulier, Femtosecond Laser Pulses, Fundamentals of Attosecond Optics by Shang, Diels and Rudolph's Ultra Short Laser Pulse Phenomena and the Principles of Optics. Once again, I am ever so grateful to Professor Trebino for his inputs and shared material. So, this is the way this entire module has unfolded. We described femtosecond laser pulses, and indeed a lot of this is true for any electromagnetic pulse in the time and frequency domains, where we also discuss the mathematical formalism, the instantaneous frequency and phase terms and the interpretation, which is still sort of ongoing. And in the previous lecture, we looked at chirp, linear, quadratic, and just made our way towards higher order chirp. Today, we will further this agenda and then go towards appreciating the concepts with regard to propagation of pulses and the time bandwidth product. So, let us jump in. So, this is our notion of an optical pulse, a realistic optical pulse with a nearly Gaussian envelope and a chirp, which later on we realize that this is a good example of linear chirp or a quadratic variation of the temporal phase with respect to time. We do not have any higher order variations evidently in the way in which this pulse has been shown. But as always, pegging ourselves on to the time domain description of the real electric field of the pulse and describing this in terms of the envelope, which is the square root of phi of t, the carrier frequency omega naught, and the phase function phi of t, which captures variations on slower scales of the phase than the carrier frequency, are the three important components. We can equally describe this equally completely and rigorously in the spectral domain, where the spectral intensity function or the spectrum plays the role analogous to. Okay, so let us resume. So, we had this time domain description of the mathematical form that captures everything about an electromagnetic pulse. The real electric field which is a real quantity, is described by three functions: an intensity function in the envelope, a phase function, both of which vary slower in time than the sinusoidal as oscillations of the carrier wave at a frequency omega naught. Okay. Likewise, take this expression, Fourier transform it, go to the spectral domain, and you get an equally complete, rigorous and legitimate description of the same electromagnetic pulse, where the role of the intensity is in time is replaced by spectrum or spectral intensity, and the temporal phase by the spectral phase, owing to the real nature of the fields and the fact that you have the term plus its complex conjugate. We get two pieces in the Fourier transform, which is S omega minus omega naught, and the other necessarily on the negative frequency side, because both omega and omega naught being frequencies are positive definite, and the two negative signs here show us that this is on the negative side of the 0 of the spectral scale. Although both these contain the same information, and we observe that we do not have negative frequencies in the normal real world, but then we would have we would just carry this over owing to the way in which we we designated things in the time domain and the fact that the field here is real. If we had started with an what I may call an original frequency domain description of the electric field, we would have written out something like this plus a CC, and when we went to the time domain we would have had something analogous in the time domain that is on either sides of the time scale. So, these are owing to mathematical conventions and description that we have used here. So, the instantaneous frequency which we have now become hopefully experts in is a sum of two terms, one the carrier frequency which is the larger value among the two, and the second which is the derivative of the phi of t term. So, omega instantaneous is omega naught minus d phi by dt. Likewise, omega has this 2 pi factor over nu the cyclical frequency, which is nu instantaneous would be nu naught minus phi of t. So, here one could add a word on the units that one must use, which we also alluded to a bit in the previous lecture, wherein if we write this in terms of angular frequency, since we measure angle in radians, that is the standard unit. So, we have on all these terms should identically have radians per second as the unit, or radians hertz if you like. But then if you wrote this in terms of nu the frequency, it would be hertz, hertz and hertz in all the three terms. So, one should be conscious of that. So, the group delay, which is the analog of the d phi by dt term, where phi there was the temporal phase, here phi basically here the phi is in the spectral domain. So, this is phi of omega. So, d phi by d omega is group delay. So, this is the typical result we use, and we also had group delay, the dispersion in group delay and so on, but we will come to that in a second. The Taylor series expansion of the phase function phi of t is contains Fourier coefficients phi naught, phi 1, phi 2. Phi naught is the absolute or initial phase or the carrier envelope phase, if we choose to define it through the C phase, C being carrier envelope, whereas phi 1 is the instantaneous, is related to the instantaneous frequency. In fact, it is computed at the 0 of time, at t is equal to 0, which is in some sense notionally the center of the pulse, or a quantity that is related usually to the maximum in the real amplitude function or the envelope of the pulse, right. So, this is again a lot of the discussion presumes an intuitive notion of well behaved pulses, and we would also be using this formalism. Nonetheless, consider really very general pulse phenomena which may not even be repeatable, like any broadband source will be emitting pulsed light, although it may not be repeatable and predictable, in which case we would not call it to be a well behaved emission. But these are of course terms with certain connotations. So, we carry such a Taylor series approach even to the frequency domain, where in the frequency domain here we have phi of omega, the spectral phase, to be again Taylor expanded in terms of phi naught, which is identical in both domains, spectral and temporal, and then phi 1, here phi 1 is the group delay at omega at the value omega naught for frequency, whereas phi 2 again computed at the central frequency omega naught, since these pulses have a spread of frequency where the spectral amplitude is non-zero, is the group delay dispersion, the GDD. Okay. So, this is the frequency domain description. The 0th order phase in the case of very short pulses, few or a couple of cycles underneath the envelope, has the physical significance of a descriptor of the shape of the electric field underneath this envelope. Whereas, if you had a few more cycles, 4 or 5 cycles in underneath the envelope within the full width at half max, we probably will not have very distinguishable shapes of the electric field, or if we use such pulses, it may not work out to try and do field sensitive measurements or measurements sensitive to the shape of the electric field of the pulse. The shape of the electric field of the pulse, once again to emphasize that, has tremendous meaning when we consider pulses which are just a couple of cycles, which contain just a couple of cycles, or in this case even just one cycle underneath the envelope within the span of the full width at half max of the envelope. Okay. So, there we could talk about the black line, which we can call a cosine pulse, because the relative phase between the maxima of the envelope and the carrier are both identically 0, whereas a relative phase shift of pi over 2 between the maximum of the envelope and the nearest field maximum of the carrier wave on either side of the envelope's maximum is pi over 2 here. It's then a sine pulse, and you could have another cosine pulse, or with a phase shift of pi, it's cosine plus pi. So, where the phase shift is indeed pi between these two markers that we place, one on the envelope and another on the carrier. Okay. So, this essentially is foreseeably important in certain scenarios, but then the game begins with considering the first order phase in frequency. The first order phase in frequency being non-zero or having a finite value such as minus 20 femtoseconds over here. Essentially, the difference between a scenario of 0 and minus 20 is the fact that in this case, true to its term, true to its name, the group delay, right, this group of waves is delayed with respect to the phi 1 is equal to 0 group by an amount minus 20 femtoseconds. So, as I said, this could be visualized as a delay caused by a delay element, such as an arm of a interferometer, like a Michelson interferometer. So, you can delay either group by simply shifting one of the arms back to increase its effective optical path as compared to another one. But then in this context, if we fix the spectral phase scenario to be flat and 0 in one scenario, and the other it is essentially the spectral phase function is linear in frequency. Of course, here we must note that phi 2 and higher order terms are set to 0 in this for the sake of creating an instructive example here. Whereas, if we now had non-zero phi 2 in the spectral phases expansion, Taylor expansion, we would start chirping the pulse, which is a more real world real pulse. Okay, because as we discussed earlier, chirp, linear chirp, this is called linear chirp, where phi 2 is non-zero, but phi 3 and higher order Fourier coefficients in the frequency domain are 0. So, this is the case of a purely linear chirp, which even dispersion can cause the pulse to have just normal plain vanilla dispersion, but we also have the concept of normal versus anomalous dispersion. Dispersion is dispersion can take an otherwise unchirped, that is a pulse with a flat spectral phase profile, merely by propagating through a medium and experiencing the dispersion in the medium, can turn into a pulse that carries a linear chirp after some finite amount of propagation. Okay. So, this is a very essential consequence, and in order to describe such a scenario for a Gaussian pulse which is linearly chirped, we took a Gaussian amplitude function with a constant E naught multiplied by the exponent of minus t by tau g square. Tau g is related to the full width at half max of the Gaussian. Tau g itself is half width at 1 over E for the Gaussian, that is it subscribes to that definition, and it is exactly the value tau g, and you can relate this to the full width at half max of the Gaussian using the factor square root of 2 log 2 log in being not base 10, but base E here, and the exponent, then the complex exponent has two terms. One is of course the carrier wave term, and the other is the term that leads to the linear chirp, the chirp coefficient here being beta. So, beta times t square, right. So, now the instantaneous frequency of the pulse as a function of time can be deduced by taking the derivative of this phase term omega naught t minus phi of t. Phi of t is in this case minus beta square t. Look back here, we have a plus sign ahead of beta, and if beta is positive is greater than 0, the way it is set here, then we essentially have an instantaneous frequency, which is written in terms of omegas, omega naught minus d phi by dt. Okay. So, what this does mean is that, once again, a point that I would not mind spending 30 seconds on in terms of emphasizing this, is the fact that here the time scale, the scale of time has 0 more or less at the center, or at demarcating the maximum of the envelope function. So, that on one side t, the time variable is time axis has positive and the other negative values. As a consequence, if I begin with an instantaneous frequency omega naught, okay, if I label the frequency nearest to the 0 of the time scale to be omega naught, then for values of negative time, the instantaneous frequency deviates from the carrier frequency central. This is the carrier frequency. I notionally use the term central frequency. We can also consider this to be a frequency central to the pulse, about which the other frequencies are spread about. So, we can call it the central frequency, or the corresponding wavelength as the central wavelength, another terminology which slipped out of my tongue, but it is a good time to introduce such slips of tongue, which are also conventions for among practitioners in the field. So, then 2 beta times t, okay, where if t assumes negative values, then the frequency slips by this factor on the instantaneous frequency slips by this factor as we go further away from the maximum of the envelope towards increasingly negative values of time, or vice versa in the case of walking on the positive axis. Of course, here it goes without saying that all this is being worked out in a frame of reference which is co-moving with respect to the pulse, which is a boosted frame, if you wish, in the language of special relativity. Now, what about a negatively chirped pulse? If beta is we can allow beta to be negative, it can be, why not, in which case then we would have a negative definite, I mean beta, if you wish, beta being less than 0. So, we express this as minus the absolute value of beta itself, then the instantaneous frequency is omega naught minus 2 the absolute value of beta times t. The converse happens, we saw this. Now, once again, if we recall, or rather take stock of where we are essentially talking about the Taylor expansion up to this scenario where, for whatever reason, there is group delay dispersion. Group delay has a frequency variation, which, as I pointed out, is merely originates from the fact that the refractive index of the medium, or if you like, the susceptibility, the first order susceptibility of the medium, are both frequency dependent quantities. Okay. Now, we looked at the Fourier transform of the of such a chirp pulse and realized that the Fourier transform essentially for a pulse with a width with a full width at half max proportional to 1 over the square root of alpha, okay, which when Fourier transform the width of the same pulse, which has a Gaussian amplitude function also in the frequency domain, okay, essentially has a factor. Here the width itself is related to in the spectral domain. So, the delta omega in the spectral domain is, I would use the sign proportional to, because of how I define delta omega. Is it half width at 1 over e, is it full width at half maximum, and so on. Choose whatever it is, they would only differ by a constant factor. It would essentially be related to you can say alpha plus alpha square plus beta square divided by alpha by 4, right. So, this would be the case in the case of a Gaussian pulse with a linear chirp. Of course, the relation between the widths in in this temporal and the spatial domains should have certain a sense to it in the spirit of Fourier transforms which we had discussed about. So, delta t being proportional to 1 over the square root of alpha, okay, if at all I can distinguish between these two signs while I write. So, likewise we would have some descriptors in the case of for a Gaussian function and for other functions when we consider these two quantities. So, we computed the group delay for a chirp pulse, and we realized that the group delay which is d phi by d omega, in this case we just had the we did not even have the phi naught to be a finite value anyway. When we take the derivative, that vanishes. We did not have we forced phi 1 to be 0 in this case, because it simply does not matter, it is just a shift in time. So, real action starts with phi 2. So, considering a phi 2 that is related to the beta which is present here, we computed the group delay and it is beta by 2, it is this expression beta by 2 divided by alpha square plus beta square multiplied by omega minus omega naught. Okay. So, this delay and frequency are linearly related. In fact, the what should I say, the shift of the frequency from the central frequency omega naught, we can call it the detuning from omega naught, is what really matters for the group delay. The point was made that the group delay and instantaneous frequency, though they are sort of analogous quantities, are not really inverses or not reciprocally related in terms of mathematical exactness, whereas for alpha the quantity, okay, which is related to the width of the pulse in the time domain, right. This, whereas for fairly long pulses where delta t tends to infinity, ergo alpha tends to 0, we would then have then the group delay and the instantaneous frequency can indeed turn out to be inverses mathematically of each other. And with these are, as I explained in the previous lecture, relatively long pulses as compared to the cycle, the optical cycle that the carrier wave has in this given scenario. Okay. So, now we considered this example, and it is worth spending a couple of minutes on this today. The Gaussian intensity of a pulse with a linear chirp of, we have here 14 radians femtosecond square. Okay, now this is something I must explain for the units that we use. So, we have phi 2 to be d2 phi of omega, that is divided by d omega naught, or in this case, computed at omega naught. Well, here phi 2, the units of phi 2 which we use here is radians femtosecond square. Okay. So, in the previous lecture I was talking to you about defining phi 2, the units of phi 2, and we considered the fact that the denominator is omega and omega has units of radians per second, right, because it is angular frequency. However, this is a matter that we must pay careful attention to when we deal with ultra fast optics literature. Here we have chosen the GDD's units to be radians per femtosecond square. But if you look at other even reliable sources, I would bring this up to you. There is a very nice website called Encyclopedia of Photonics, it is RP Photonics. It is a very good resource. I would recommend you to use this free resource online. Now, over there GD phi 2, that is GDD, and also in other sources and literature, you will see the units of GDD are just second square or femtosecond square. I mean, femto is just, I mean, to keep things reasonable. Otherwise, the same quantity 14.5 expressed in second square would have 10 to the minus 30 multiplied to it, which is unnecessary. We just use the femto instead of that. Okay, so is one right, the other wrong? Actually not. Okay, it is owing to the way in which we have chosen to define this quantity. Is this radians times femtosecond square also absolutely perfectly right? It is right, but one can also choose other ways of expressing the same. So, what is the mess here, or what is the problem? So, in defining this sort of a quantity, right, we essentially have to choose between whether we are expressing the frequency dependence of phi as frequency dependence in omega units, which is radians per second, or whether I am using nu for this. Well, I have the confusion, if anything, arises here out of the following fact. It arises out of the fact that somewhere in describing all the stuff that you see on the screen, look at the frequency axis and units that we have used here. We have used one femtosecond inverse, not second inverse, right. So, maybe I write this also over here. Or this is well, we are talking about omega. So, omega is radians times femtosecond inverse, this is femtosecond inverse. By choosing frequency to be femtosecond inverse, we have implicitly chosen to describe everything in terms of nu. Okay. So, factors of 2 pi radians which get multiplied in the case of omega need to be done away with. Okay. However, the reason that this is radians times femtosecond square is because we have phi of omega to be phi naught plus phi 1 times omega minus omega naught, or in this case we have chosen nu. So, it is nu minus nu naught plus phi 2 times nu minus nu naught square, right. Now, the units on the left hand side, phi is measured in units of radian, all right. So, therefore, here I should have taken this to be nu. So, to keeping this entire thing consistently, and here we have set the units for phase being measured in radians, right. So, therefore, we have this. Well, had we used something like degrees, we may not have bothered about it, then maybe we just use it as femtosecond square. So, owing to this fact, typically to disambiguate it in literature, sometimes, not sometimes, conventionally people use femtosecond square or second square for the group delay dispersion, but beware of what we are doing, be aware or beware, both are equally good here. So, that is the second order phase and linear chirp, where in this case we have chosen phi 2 to be positive 14.5 radians femtosecond square. As a consequence, since this is the case over here, we of course have a parabolic opening for these guys in the frequency and in the time domain. So, you see that we have an increasing parabola here as the phase goes sweeps up from 0 upwards, okay. Whereas this translates to a downward opening parabola when Fourier transformed. And please pay attention to the fact that all this is nice, neat and clear in the frequency domain. If we transform these into the wavelength domain, then a little bit of hell breaks loose. It does not seem to resemble anything that we are talking about, neither Gaussian nor parabola. That is because of what we have here, right. I mean, the scale has a Jacobian, which is not linear, it is not a linear relationship between frequency and time domains, and that marks its presence by a skewed Gaussian and also a skewed parabola for the phase profile. Okay, so a negative linear chirp, just putting a negative sign with for the same phi 2 term of the same magnitude results in a downward opening parabola over here, right. And the rest follows, the rest is quite similar, okay. So, so basically we can play around with these, and if you have a good plotting program like MATLAB or Python at your disposal, this is something easily done in these cases, okay.